Hello guys, hope all of you are doing well. Last time we discussed the problem of inverse dynamics, and we said the goal in inverse dynamics is to be able to find the individual joint torques and the forces that are present in the various joints of a robot. In that case, the knowns are the position of the robot. So if I know the position of the end effector as a function of time, I will be able to solve for the individual angles or joint angles, theta 1, theta 2, and theta 3, and then differentiate those and then differentiate one more time. Basically, I'll have omegas, and I'll have the alphas, like the angular velocities and angular accelerations of the various joints. And the problem of inverse dynamics is we separate the various links. We draw a free body diagram on every link, and we draw an inertial diagram also on every link, where we put MAG at the center of gravity, and then we put IG alpha. Please do watch the last lecture that I posted because it has very important information on inverse dynamics. And ultimately, we said we're going to calculate the acceleration of the center of gravities, and the way we did that last time is we found the x position. Let's say you're trying to find the acceleration of point g1. Basically, you will express the x as a function of the variables, and then you use chain rule to be able to obtain the velocity in x direction and acceleration in x direction, and then you do the same thing in a vertical direction. So please do watch that, and we went through these steps in detail last time. Okay, so today we're going to look into another way for finding the accelerations on the various links. Well, we know it's pretty straightforward to find the acceleration by differentiating the position, just like what we did last time, like sort of like the analytical method for computing velocity and acceleration. Let's say you want to find the acceleration of point Q3. Obviously, you're going to have an acceleration vector, but this acceleration vector has an x component and it also have a y component. To find the x component, all you do is you express the x position here as a function of theta 1, 2, and theta 3. Now it becomes a multivariable function. When I differentiate that, I will apply a chain rule basically. Essentially, I'll apply the partial derivative of this position as a function with respect to theta 1 multiplied by theta 1 prime plus partial derivative with respect to theta 2 multiplied by theta 2 prime plus partial derivative of this guy with respect to theta 3 multiplied by theta 3 prime. So we've already won that. So today we're going to look into vector dynamics, and it is actually possible to find the acceleration vector using this equation that we have here. So this equation is a recursive equation that allows me to find the acceleration of any point on the rigid body, including the acceleration of gravity. So this enables me to find the acceleration of any point on the rigid body if I know the acceleration of one point, right? So I need to know the acceleration vector at one point on the same rigid body. And I also need to know the angular acceleration of that rigid body and the angular velocity on that rigid body. So you need to know alpha, like the rate of, or essentially starting at omega is the rate of change of the angle theta with respect to time of a rigid body, right? And then you need to also know alpha, and you need to know the acceleration of one point. So once you have this, you can basically find the acceleration of any point on a rigid body. And here, alpha and omega, they have to be absolute, meaning that alpha is being measured with respect to a non-moving frame, and likewise omega, right? So let's start by finding the acceleration of this point, g1, which is under regard of the first thing. So we're going to use this equation. Well, I need to know the acceleration at one point on that rigid body. So we know it's all moving except that this point here, right? So the point that intersects the z0 axis will actually have a zero acceleration because it's not moving, right? So this is going to be our zero reference, or AO. So this is point O. It has zero acceleration. So now we're going to just do this, right? So you'll do alpha, which is theta 1 double dot in the k direction, right? So theta 1 double dot, k direction, cross product RG1 with respect to O. Now, RG1 with respect to O is a vector that points from O to point G1, right? So it's a vector that points from O to point G1. And then what are the coordinates of that vector? There are the length of this guy, right? Which could be, for example, L1 over 2. In the x direction, the component of this vector in x direction is L1 over 2 cosine theta 1 I in our direction, and then in the j direction, we're going to have L1 over 2 sine theta 1 j. So now you have this, you can do the cross product of this guy. Last thing here, we have omega 1 cross omega 1 cross RG1O. When the movement is planar, when the rigid body is moving in a planar plane, then omega 1 cross RGO will also omega 1 cross omega 1 cross RGO will actually be equal to minus omega square RGO with respect to O. So you will basically knock down all of these because this ends up being the centrifugal acceleration, right? And so omega 1, so we know that omega 1 is theta 1 prime, right? And we already can calculate that. RG1O, we know it. So now we have the acceleration of this point G1. Now, if we were to find the acceleration of point G2, and by the way, once you calculate the acceleration of point G1, you are good, right? So we'll have so before we calculated the acceleration in x direction by doing the double derivative on the position along the time, I will simply use that vector, right? Once you find this, you're going to have I components plus something j component. So the I component will actually be equal to your AX, and the j component will be the AY. Now, to find the acceleration of point G2, how do you do it? Well, you need to find the acceleration, or you need to know the acceleration of another point on that rigid body. And the best way is to use your reference is this point, right? And this is point 0.01. This is point 0.0. This is point 0.01, which is the center of frame 1. Well, how do you find the acceleration of that point? Well, you can use that rigid body, right? We already know alpha here, we know omega. We can use this distance to find the acceleration at this point. Now, to find the acceleration of this point, you'll also use the same thing recursively, right? And then we say the acceleration of point G2 is equal to the acceleration of point 0.01 plus, now you're going to do alpha 2, right? So alpha 2 cross RG2 with respect to 0.1, right? Minus omega square cross, or minus omega square RG2 with respect to 0.1, right? And now alpha 1 is going to be an absolute angular acceleration, or alpha 2 in this case, right? So alpha 2 is an absolute, so it cannot be measured with respect to x1. It will be equal to theta 1 double dot plus theta 2 double dot. Why? Because theta 2 has to be absolute, and for this angle to be absolute, it needs to be measured with respect to a non-moving frame, which is only x0. So this angle needs to wrap all the way around x0, right? So alpha, so finding the acceleration of point G2 will be equal to the acceleration of this point, so A01 plus this alpha 1, which is equivalent to theta 1 double dot plus theta 2 double dot cross RG2 with respect to O minus omega square cross RG2 with respect to O. And what is omega, by the way? Omega again is equal to theta 1 prime plus theta 2 prime, right? So because again, this also have to be an absolute value. Not an absolute value, it has to be measured with respect to it has to be an absolute velocity in the sense that it's being measured with respect to a non-moving frame. Okay, very good. So that is that, and so same thing here. So this is how we did that basically. Okay, so just quickly to go back. So AG1 is respect to AO plus that. So here we calculate the acceleration of point G1, right? So I'm going to go a step. Then I can find the acceleration of point 0.01, right? Is equal to the acceleration of this point O plus, recursively. So now I found the acceleration of this point. Now, one more step. Acceleration of point G2 is equal to the acceleration of point 0.01 plus alpha 2 cross RG2 respect to O. So this is my alpha 2 and this is my omega 2. Why? Because it has to be an absolute value. So we're literally adding them up. Okay, last thing is acceleration of, we need to find the acceleration of point G3, but I can't because it's not on the same rigid body. I need to find the acceleration of this point, then jump from here to here. So it's recursive. So you start here at the base, you go up, you come here, then you use this point to find the acceleration of that point, then you use the acceleration of this point to find the acceleration of that point. Okay, now AG3 is equal to AO2 plus alpha 3 cross RG3 with respect to O2. RG3 with respect to O2 is a vector that, points from O2 to G3, right? So this is like this is point G3 as viewed from O2, right? So it's that vector right there. Regarding the accelerations, you would have to add them up. So it's theta 1 double dot plus theta 2 double dot plus theta 3 double dot, right? Because you can't just, you can't just say it's theta 3 double dot. Why? Because this thing is sitting on this platform, and these guys could be also accelerating, right? So we need to find the net angular acceleration. Okay, great. So regarding inverse dynamics, we kind of been touching on that here and there with a few examples. So one last thing here is, always here the free body diagram on this guy start with link one, and this is what we did last time, but for only a 2-degree freedom robot, we put the forces. So whenever you have a motor, you're gonna have a torque. You have OX and an OY because this is in a planar plane, right? And so these are the reaction forces which are applied on the motor housing, right? So these are the forces that the bolts that holds the motor to a fixture, right? O1x, O1y are the forces that this link one applies on the housing of motor two, right? So the housing of motor two is rigidly connected on link one, and the shaft of motor two is attached to link two, right? So it's rotating with link two, right? But the motor is actually connected. So these are the forces that the bolts on motor two are actually taking to compensate for that acceleration. So whatever acceleration you have here, you're going to respond here with these forces, right? That's what Newton is telling us. On the right figure, we're going to have IG1, alpha 1, MAG1. This is our total acceleration vector, right? With the method that we've learned, we're going to get the acceleration in the x direction, and then we're going to get it in the y direction separately. And alpha is what? Alpha is absolute angular acceleration. Angular acceleration is not for a point. Angular acceleration is for a rigid body or for a line, right? So if you have any arbitrary line, you can measure the difference in the angle. You can make that line infinite, right? And then you can draw any other line, right? Horizontal, vertical, any direction, as long as it's fixed. And then you can kind of keep track of how that angle is changing on that rigid body, right? So you keep track of it. One time you get the velocity, you keep track of the velocity of that angle with respect to time, you get the angular acceleration. Okay, so same process. It's very repetitive, very systematic, and this is how I would like you guys to apply this process on an exam, right? So it's very important that you draw this nice and clear. I want to see all the forces, all the torques, force of the gravity, very important. And then on the right figure, I want to see this. So those of you who try to merge these two figures into one, they will definitely lose points. If you don't have this figure, you will lose a lot of points. And the worst thing that you could do is just not have any figure. You know what I mean? So it's extremely important to actually have this exactly the way that I have it here. And one last thing here. So let's say you assume the forces, right? So when you start solving the problem, you don't even know the direction of the forces. So we're going to assume them like that. And later on, when you put it in matrix format and then you solve it, and then if O1x was negative, like you type it in Matlab, you solve it, O1x is negative. It means that it is in the opposite direction of what you have assumed, right? It's not in the opposite direction of your original frame. No. Okay, so this is very important as well. Same thing for link 3, right? So link 3, we introduce this load P. This is not an unknown because here I can only solve for one unknown in the vertical direction. If I gave you O to Y, then you would have to, if I provide O to Y, then you can solve for P, right? But if you're trying to solve for O to Y, then you need to know P, right? Because now you would be introducing two unknowns for a single equation, that is summing the forces in the vertical direction. Okay, so that is very important. And one very little thing as well here is that obviously here we're assuming that we know the accelerations. But let's say, I didn't give you the accelerations. I didn't give you the acceleration, but I gave you the forces. So it's the same thing, right? So you can actually solve for the accelerations for these forces. So this is like inverse dynamics and then forward dynamics. Forward dynamics, which we're actually going to discuss in a minute. If you have these forces, you will be able to actually find, the accelerations, the instantaneous accelerations, right? Just like you have F is equal to ma, right? If I told you that, I'm pushing on this object with 20 Newton, what is the acceleration? F is equal to ma, a is equal to F over m, right? So same thing actually applies here in matrix form. Okay, so this is what we did before, but for only a 2DOF robot. Now it's 9DOF robot. I'm sorry, it's 3 degrees of freedom robot, so you have 9 unknowns, right? So what we do, these are the equations that we do. So I'm going to go over now the MATLAB code. So the MATLAB code starts as follows. right? So you're gonna, so this is my force peak. So force P, M1, M2, M3, the masses are J1 to J3 are the rotational inertia, which is in units of kilogram per meter square, right? Link length, so this is, you can vary that. I have my initial velocity, omega 1, alpha 1, and basically my thetas, right? So this is where the robot is starting, and I'm trying to basically here solve the inverse dynamics of this robot, right? And here I'm literally basically changing a time increment. So t is equal, so this is my time is equal to 0 initially, and then this is my time step. And what I'm doing is basically I am basically forcing some particular theta, theta 1, theta 2, theta 3 as a function of time, right? So these are my thetas, theta 1, theta 2, theta 3 as a function of time. And as a result of that, I'm actually getting my omegas and my alphas. Does that make sense? Right, so I can specify, this is a movement. I'm not doing any inverse kinematics here. I'm simply working in the joint space, right? And I'm specifying what I would like for thetas as a function of time. I find my omegas, and then this is my alpha. Then I go ahead and I do my rotational transformations, and then these are pretty simple. So in this robot, basically, you simply rotate about z and then you translate along x, right? So we've done that a lot, right? So this is my robot. So simply rotate about z, translate about x. Rotate about z, translate about x. Rotate about z, translate about x. If you want to find the coordinate point G1, you rotate about z, you translate by x by how much? By simply ln over 2, right? This is how you can find this homogeneous transformation between frame O and then some virtual frame at point G1, so you can use that to find the coordinate of point G1, right? Because you would need those for finding the acceleration, right? But here what I did is simply I find T01, T02, T01, 1, 2 to 3, right? Find my homogeneous between frame 0, frame 3. Very simple. Then I can find the coordinates of these points, 03, 02, 01. Then what I'm doing here is, so there are two ways, right? One way would be to do the differentiation, right, using the chain rule. Here I chose to actually do the vector dynamics, right, which is doing the cross product, right? So AG1 is equal to A0 plus alpha cross RG1 with respect to O minus omega square RG1 with respect to O. So you can actually do that in Matlab. And these are my absolute angular velocities, right? I said all these angular velocities, they have to be absolute. And because of, the way we do the frames, etc., transformations, basically, we are doing just relative angles between the various things. So these have to be, when it comes to dynamics, the position have to be absolute, right? So that is why I have omega 1 is equal to that. Omega 2, I'm basically adding them up, right? And then omega 3, I'm also adding them up. Why? Because omega 3 is equal to omega 1 plus omega 2 plus omega 3 as vectors, right? Because link 3 sits on the second link, which second link sits on the first link, right? So the angular velocity is what? The angular velocity is, kind of builds up, right? So even if omega 2 and omega 3 are not changing, but omega 1 has some velocity, actually link 3 will have the same angular velocity as the first link, right? Why? Because you're sitting on the first link, even though omega 2 and omega 3 are 0, right? You are still moving because you are sitting on the first link, right? Same thing for the angular acceleration. Now what I'm doing here is ROG1. Simply I'm expressing the vector ROG1, right? Which is L1 over 2 cosine theta 1, L1 over 2 sin theta 1. So this is the x component of vector of point G1. Same thing, this is 0.01. And this is, so here, this is what I'm doing, right? So acceleration of point G1 is equal to acceleration of point O plus alpha, right? So so this is basically alpha cross ROG. And this is, very interesting because you can actually do a cross product in Matlab using matrices. And this is actually nothing but a skew symmetric matrix. So if you do S of alpha, simply multiply this 3 by 3 matrix multiplied by ROG1, you will actually, as if you are doing the cross product of alpha cross ROG1. And we've actually covered the skew symmetric matrix in a previous lecture, right? What is the skew symmetric matrix, etc. Let me quickly reshare that to show you what is a skew symmetric matrix. And okay. Okay, so this is my skew symmetric matrix, right? S of Q. So you notice the zeros here. So you can, if you multiply this guy, right? So this would be your alpha. Like S of alpha, you have alpha X, alpha Y, alpha Z, right? So multiply this guy by the vector ROG1, right? Which has, Rx, Y. So this is X and then Z component. This is like you're doing cross product. Or you can use simply the cross function in Matlab, would actually do the same job. But I choose to do that. Okay, so here, so this is that. If I wanna do omega square times, right? So minus omega square RG1, right? The last component, I can actually do skew symmetric matrix again. Or I can, so this is what you would do, right? If you are doing omega square. Why? Because so it's omega cross RG, right? So legally you can do this array operation 3 by 3 multiplied by 3 by 3 multiplied by, or you can do you just use a cross product function in Matlab. So either way will actually work. So I encourage you to actually look into that. All right, how you actually do this. So we found acceleration of point G1, then find acceleration of point O1. So we can use that to recursively jump and then find the acceleration of the second point. So acceleration of point G2 is equals acceleration of point O1. Right now we're on the second link. We're going to use a frame O1, and then we're going to do the same process, right? So alpha cross RG2 with respect to O1 plus omega cross R with respect to O1, right? So this is why you actually have first one, use the cross product first, and then you do cross product one more time. And the same thing for this last part. So this is very repetitive here. So once you have the accelerations, obviously you would need to do that on a paper, just like what we did last time. You put it in matrix format on a paper, right? And you can, once you have your equations, right? So we have here non-equations. We can put them in matrix form. So this is my matrix A, and matrix B will actually have the accelerations, right? So here, instead of me, doing that by hand, now I can do this part in Matlab. So, after you do the analysis, you'll see that, B1 was equal to, so this is the first equation, right? So the first equation, right, equal to, so left side, right side, the knowns are here, right? M1 multiplied by acceleration of point G1, 1 in the x direction, right? Because this is a vector. That's what we did before. So, and this is my B2, this is my B3, pretty straightforward, right? So this is nothing but, right, putting the equations in matrix format, right? We have Ax is equal to B. B is going to be equal to the knowns, and we know all the knowns, right? Which are the accelerations or gravity. And this is my B here. I put that in a matrix, and then X here is basically now I'm solving for the unknowns, right? So this is my X, and that's it, right? So after I solve for X, X is basically equivalent to what? OX, OY, O1X. So basically, these are the entries of the X vector. So once you have that, basically, you are good, right? The rest here is basically just more like kind of, organization to basically plot it, etc. Try typing this code, or actually you do it on your own, so you really understand that well. I actually posted new assignments, and they will actually involve inverse dynamics of 2 degrees of freedom robot. So you'll actually learn that as you do the assignment, which is also obviously included in our second midterm, right? Okay, so that is it, guys, regarding inverse dynamics. Next time we'll start looking into forward kinematics. I'm sorry, forward dynamics. Any questions, guys? Please feel free to reach out to me by email. I'd be very happy to set up, time on Zoom call to go over, any questions you may have regarding the course, regarding, the Matlab portions of it. If you're having hard times understanding, inverse kinematics, frames, how to put frames, how to put the z-axis, how to, draw proper DH frames, how to find the Jacobian, how to interpret the Jacobian, how to interpret singularities on a robot, all that stuff, please do feel free to email me and then I'll be very happy to help you out.